Hello. Welcome to Spectroscopy. Hi there. Thanks for letting me know you can hear me. It's great to see you guys. While I'm waiting for a few minutes to get started, here is a link to the slides that I'll be using, just so that you have it. I'll post it a few times. I hope everyone is doing great. Just gonna wait one more minute, take a sip of coffee, and get ready for this. You can't download it, but you can access it at that link forever. So just bookmark the link and you'll have access to the slides. Okay, let's get started. Um, just to make sure you can hear me, right? Thank you so much. Okay, on the left-hand side, I have a QR code for our mentee, and I put a few interactive questions through here. If you want to participate, feel free. If you don't want to participate, that's fine too. I just know it's hard to be talked at for a long time, so I wanted you to have a chance to show me what you know. And if you want to ask questions, feel free to use the Zoom chat. I'll have that open the whole time. And if I give you a couple minutes to think about something, I'll be in the chat answering questions as fast as I can. So I hope this goes great, and don't be afraid to just let me know what you need. So the general plan for today is to really quickly kind of go over how we might deduce the empirical formula of something given percent composition or some other sort of stoichiometric data. And then to remind you a little bit about IHD. That's about sort of how many hydrogens you could add into a molecule to make it saturated. And that's going to be a hint about ring structure or multiple bonds. Then we're going to get to the meat of it. That's spectroscopy. We'll start with IR spectroscopy, looking at the vibrations of molecules. We'll move to mass spectrometry, uh, breaking molecules into tiny little pieces and seeing what they're made out of. And then NMR spectroscopy, that's going to be really how we deduce the structure of most molecules. Finally, the students who are taking this class at SL aren't responsible for what's called spin coupling or high resolution spectra. So I tried to break it down into two parts and put that high resolution stuff at the very end. So if you are an SL student, you might want to stop, or you might want to stick around. It's pretty interesting, and it's not a really big section of it. The HL content is kind of sprinkled through, but the biggest difference is that spin splitting. So definitely going to be at the HL level for you HL people. But again, like focusing on the spin splitting is really at the end. X-ray crystallography is not going to be included. The questions on past papers really just pertain to what you can learn from X-ray diffraction. And the answer there is going to be you can learn the lengths of bonds and the bond angles. So it's like taking a picture of a molecule using X-rays, because X-rays have a wavelength that's really, really similar to the size of a molecule. Since there have been so few questions across the past 15 years, I didn't think that it was worth spending a lot of time on in this session. Okay, so empirical formula, as you recall, is going to be the simplest whole number ratio of atoms in a molecule. And there are sort of two paths that we can use to identify the empirical formula. One is the easier one, where they just give us percent compositions, and one is the more challenging one, where they do some sort of combustion analysis, and we need to go through a few steps to deduce that empirical formula. So I have a quick example of both, and then I'm going to have you guys work out if you're interested, another one. So I'll just give you a minute to work and address the chat while I do that. The session is going to go on for at least 90 minutes. It's pretty flexible. So back to the question. Sorry, I'm getting distracted already, but we're back on track. If someone gave me those percent compositions, the way I would approach this problem is I would assume that I had a known mass of the stuff so that those percents by mass could be turned into grams. And because I am a simple person, I like to choose that I have 100 grams. So if I have 54.52% carbon, that would be 54.52 grams of carbon. 9.18% hydrogen would be 9.18 grams of hydrogen, et cetera. And so I could take those mass values and convert them into mole values by using the molar mass. And so I've taken the mass percents and now I have the moles. The empirical formula is going to be the smallest whole number ratio of atoms. So it's going to be the smallest whole number ratio of moles of atoms. And we often determine that by dividing through by the smallest number of moles that we see. So the smallest number there is the moles of oxygen at 2.27. I went ahead and dividing all my molar amounts by 2.27, and I got a ratio of 2 carbons to every 4 hydrogens to every 1 oxygen, or an empirical formula of C2H4O. So again, that's a first step a lot in spectroscopy, where they're going to give me some sort of stoichiometric information, and I'm going to have to deduce what the empirical formula of my molecule is. We might then use a mass spectrum to deduce the molecular formula, and we'll go through those steps in a minute. If you didn't get the link to the slides, it's there again, and I'll repost it every couple of minutes as people come into the session. The slides will live there forever. And so if you have that link, you will have access to it. If we had to solve this problem in the more complicated way, where instead of giving us the mass percents, a combustion analysis is done, we're going to have to do a little bit more work. And so what a common problem might look like there is we took 1 gram of our compound that contains carbon, hydrogen, and oxygen, and we burned it. And because we did complete combustion, the products are going to be carbon dioxide and liquid water. They gave us the amounts of carbon dioxide and liquid water in mass, but we can, of course, convert that into moles. And so I went ahead and I took the masses of carbon dioxide and water and converted them into moles. But then I went one step further and I went from the moles of carbon dioxide and moles of water into the moles of the actual atoms of carbon and hydrogen, because I recognized that all of the carbon and all of the hydrogen that was in that original compound was now going to be found in carbon dioxide and water. So now I have a window into how much carbon and hydrogen is actually in the compound I'm trying to describe. Now you might already see that there's a 2-to-1 ratio between hydrogen and carbon, but we don't know enough about the oxygen yet. To determine something about the oxygen is the part of this that is a bit more challenging, because the oxygen is coming from both my organic compound and the oxygen I'm burning it in. And the oxygen is appearing in both the carbon dioxide and the water. So since the oxygen is everywhere, it's hard to identify what was actually in the compound. So we're going to do that by difference. I'm going to take the moles of carbon and the moles of hydrogen and convert them back into grams. So I could tell you that of that 1 gram of the original compound, 0.546 grams of it were carbon. Similarly, 0.092 grams of it were hydrogen. We're going to subtract those 2 values from 1, and then we're going to know the mass of the oxygen that had to be in the compound, because we believe in the conservation of mass. Quickly converting from the mass of oxygen to the moles of oxygen, we're back where we were, where we have the moles of each of the atoms, and we can find the mole ratio and get the same formula. So this is 2 ways of finding the empirical formula of the same compound. I'm going to use this empirical formula for a few examples going forward. I just wanted to show you that sometimes that first part of this problem is very much a topic 1 oriented part. And so remembering how to do empirical formula can be useful, just so that we can make sure that we can identify what the full compound is given the spectroscopic information. So Azan, you're totally right. I hope that I did well for you. And Anushka, I'm going to post that link one more time. I'll try to do it one more time around 5 minutes from now, just to make sure that everyone has access to these slides. Spectroscopy is going to come up in papers 1 and 2. It hasn't been in paper 3 quite as often in my recollection. It's really a paper 2 oriented question because the data booklet is such a rich source of information about what the chemical shift of something is, or what the fragment of something might mass. So the expectation is that paper 2 is where you might get kind of a longer form question. And I've tried to embed a lot more questions that we can work on together to model how we might answer them for IB through this talk. The recording will be posted on the Revision Village site, along with the recordings for all of the other study sessions that are going. There are some great math ones. The doorbell rang and I'm not sure what that was. So if anyone's noticing anything crazy, let me know. Otherwise, I'm just going to continue. The second thing I said we were going to sort of warm up with was the index of hydrogen deficiency, or the IHD. And to me, that formula is absolutely crazy, but it's just a quick way of trying to determine how many double bonds or triple bonds or rings there are in a structure. So you can imagine if you're trying to figure out what a structure is, one of the most nice tools you could have would be to imagine some of the functional groups that you learned in organic. And so you might say to yourself, well, if I have a nitrogen and I know I have 2 pi bonds, I think that I probably have a nitrile. Or you might say to yourself, if I have 2 oxygens and I have a double bond, I probably have maybe a carboxylic acid or an ester. So I'm just imagining those functional groups as what I'm going to be trying to look for when I deduce the structures of the molecules. To do that, the IHD is equal to 2 times the number of carbons plus 2 minus the number of hydrogens. That's like the formula I actually know. That's the formula from alkanes, where we know in a completely saturated molecule, the number of hydrogens is 2 times the carbons plus 2. So if you thought about propane for a minute, propane has 3 carbons in it, and a saturated propane molecule is going to have 3 times 2 plus 2 more is 8 hydrogens. So propane is C3H8, or we have 2 times 3 plus 2, 8 hydrogens for every 3 carbons. So the beginning of this formula, 2C plus 2, and the minus H are going to make that disappear, that be a 0. If we have the 3 and the 8, we're going to get an IHD of 0. We're going to find this molecule is completely saturated, or that there is no hydrogen deficiency. As we remove hydrogens, we're going to find, of course, that there is a hydrogen deficiency. And the way we remove hydrogens while still maintaining the octet rule is by putting in double bonds, or by making rings. Now, nitrogens, oxygen, and halogens can also be included in our molecule. And so we need to come up with a way to figure out what the IHD in the presence of those atoms might be. And so in the presence of those atoms, you can see my full formula. It says ignore the oxygens. It says pretend that every halogen is a hydrogen. And finally, you're going to add the number of nitrogens. You may memorize that. That would be my recommendation at this point. And so I put together just a little compound right here to make sure that we could plug in values and see that it works. So here's the compound written out as its molecular formula. Here's the compound written out as its full structural formula. And if things are working out correctly, the expectation is that we should, of course, get the same answer for both. So when I visualize the molecule, what I want you to see is that there are 4 double bonds and there is 1 ring. That means that my expectation is that the IHD should be 5. If I were to stretch that molecule out and saturate it, that is to say, put a hydrogen everywhere I possibly could, It would take 10 hydrogens to do that. If I look at the molecular formula, plug in the value for carbon, plug in the values for nitrogen, plug in the values for hydrogen, and for X, which stands for halogen, I get that same 5. So here's a little hint. If you see an IHD that is 4 or bigger, I want you to say to yourself, gosh, I am so sure that there's going to be some sort of an aromatic ring in there. I put a pyridine in for fun. I would expect on your exam it would be a benzene ring, because so much of the syllabus in topic 10 is devoted to understanding benzene a little bit better. So the IHD formula is one that I would absolutely flashcard for the exam. And let's see how it's going to help us out. So I have one for you to work, and I'll try to get a few questions in the Q&A. Oh my goodness. There we go. So if you have the Menti on, of course, this doesn't have a link. So if you manage to get into Menti, you can answer this question in Menti. If you didn't manage to get into Menti, I'll make sure that that link is up. And you can just think your answer and put it in the chat. Just going to give you a couple of seconds to think about this. Thank you, Mentiers. I appreciate you. So oxygen does not affect the IHD. We're going to completely ignore it. The IHD, in fact, is a measurement of whether or not a reaction or a molecule is saturated. That's exactly what it means. An unsaturated molecule will have an IHD that is bigger than 0. And for the nitrogen, you can't ignore it. For the nitrogen, you need to include it in the formula. And so the way that we do that is we add the number of nitrogens. All of you seem to be agreeing that the answer is 5. I hope what you see is this benzene is a ring. That's going to count for 1. And if I imagine benzene without resonance, if I put the double bonds back in, I can imagine the 3 double bonds in benzene. So that's going to be 3 more. And then I have the carboxylic acid with its carbonyl group. So 1 more there. And so overall, there are 4 double bonds. There's 1 ring. And so the IHD here is, in fact, 5. So the reason I chose benzene in this form was just to make sure that even though the double bonds aren't written, you know that they're there. And so it's a bit tricky. Normally, we can just count the double bonds. But in the case of benzene, we have to look at it and say, of course, if we were to write a specific one of the resonance structures of benzene, we would show it with 3 double bonds. So again, we're going to get an answer of 5 here. There are going to be 3 double bonds and 1 ring. So benzene is always worth 4, and the carboxylic acid's carbonyl is the 5th in IHD. Okay. Hope that went okay. These are 2 tools that we're going to use at the beginning. We haven't looked at any spectroscopy yet. All I'm trying to do is to look at a molecule and come up with what its empirical formula is, and then to come up with the number of rings and double bonds it has to see if that will allow me to deduce a specific functional group that I'm aware of. If you're not feeling good, remember that this is just a simpler way of trying to write down relatively quickly how many double bonds a molecule has, or how unsaturated a molecule is. So feel free to go back and look at the IHD formula that will allow you to add up the different kinds of atoms and deduce how many double bonds and rings your structure has. We are just counting double bonds and rings. I'm going to move into our first kind of spectroscopy, and that's going to be IR spectroscopy, or infrared spectroscopy. Infrared spectroscopy actually affects the vibrational motion of a molecule. Infrared light is lower in energy than UV visible light. UV visible light is the kind of light that we use to do homolytic fission of the chlorine-chlorine bond. It breaks bonds, it moves electrons. IR light, being lower in energy, can't do that. It's just going to make molecules sort of wiggle. And the way that molecules wiggle is that they bend and they stretch. Now, there are a lot of atoms in some of the molecules that we look at. And officially, there are a lot of ways that a molecule can bend and stretch. If there are n atoms in a molecule, there's something like 3n minus 6 different vibrational modes. That's a big number. But the wonder of this is that when we actually look at the IR spectra, we will find characteristic peaks that we associate with specific bonds. I'm going to show you that in just a second. So n is the number of atoms. And I'm just trying to think about a molecule that might be interesting to you. So we were talking about propane. Propane was C3H8. So there are 11 atoms in propane. If I took 3 times 11, that's 33, minus 6, that's 27. There are 27 different vibrations. 27 different, that's a huge number. And I'm not completely sure that I'm going to be able to resolve that number into anything that's meaningful. But when I look at the spectrum, what I find is that there are very specific regions of the spectrum that are associated with carbon-carbon bonds or carbon-hydrogen bonds. And I can use that to figure out what a molecule looks like. The units that we're going to use are called wave numbers. And wave numbers are just a fancy way of talking about energy. I put the formula in there in case you're nervous that the units are going to be reciprocal centimeters or wave numbers, but I've never seen calculations that rely on them. It's just going to be our x-axis in an IR spectrum. So our x-axis is going to have to do with the energy that different bonds are absorbing, and our y-axis is going to have to do with how strongly they're absorbing it. I'm going to show you some data in a second. Don't worry. So this is similar to the information that you would find in the data booklet. On the left-hand side, it's going to list bonds that are associated with the functional groups that you know. And then it's going to list the wave numbers that we associate with that bond being present in your molecule. So if you see a signal between 1700 and 1750, you're going to be able to say to yourself, all right, there's a C double bond O. Because there's a C double bond O, you might be able to then generalize that the classes of molecules that are possible for your structure are aldehydes, ketones, carboxylic acids, and esters. So this is from your data booklet. This is not something you have to memorize. And what that's going to look like in an actual IR spectrum is something like this. So I put 3 IR spectra next to each other. I want you to notice that on the x-axis, I have centimeters to the -1, and the centimeters to the -1 actually increase from right to left. So over on the right-hand side, I have small numbers, and on the left-hand side, I have the big numbers. I know that my pictures can be a little bit small on your screen, but rest assured that this big peak on the left-hand side has a absorbance at about 3,000 reciprocal centimeters or wave numbers. I also want you to notice that absorption is kind of upside down in IR. And that's because the y-axis is always plotted as transmittance. That is how much light gets through. So if no light gets through, all of it was absorbed. And so the deepest trough is like the strongest absorption. On the right-hand side, I hope you see the 3 molecules, propanoic acid, propanal, and propan-1-ol. And I was just curious how similar or different their spectra would look. And so I went back to my data booklet and I found that this carbonyl peak had a pretty characteristic absorbance between 1700 and 1750, and it was defined as strong. And so a typical question on an exam would point out that peak at 1700 and say, what is it? And your answer is going to be that it is the presence of a C double bond O in your molecule. You could also look at the third structure and see that there is no peak there. And that would indicate the absence of a C double bond O. So sometimes they'll say, look in the region between 1500 and 2000. What is not present in this molecule? Another thing I wanted to show you is that on the left-hand side, we have the OH and the COOH showing their characteristic spectra. There we go. And if I look in the data booklet, I'm going to find that there are a whole lot of bonds in that region, in the 3000-ish region. So again, that's going to be on the left side because my x-axis is in some ways backwards of my expectation. The word broad seems to be a little bit confounding to some of the students that I've worked with. So I want you to look at that first peak, and I want you to think about how little structure there is in it, how wide the peak is. That's what broad means. So a carboxylic acid has an OH peak that is extremely wide or broad. Now the one below it, the structure of propanal, does not have a broad peak. It has a peak in the same general vicinity, but I hope that you can see all of the structure in it. It's got a whole lot of really close together, but very skinny peaks. That's because there are a whole lot of carbon-hydrogen bonds that are slightly different from each other. So they all appear in the same region of the spectrum, but it is not going to be broad. And so it is not going to be a sign of an OH. It's going to be a sign of a CH. In propan 1-all, you're going to see a broader profile on the left-hand side that my red line is passing directly through. And then to its right, you're going to see that same sort of whole lot of really narrow things. So there you should see evidence of both an OH in an alcohol and a CH. In the top picture, we believe it's going to be a carboxylic acid because it's very broad, even bigger. So I wanted you just to see together the OH in a carboxylic acid and the OH in an alcohol. The OH in an alcohol has a slightly larger wave number. That's another way of discriminating between them. But sometimes that carboxylic acid is so broad, it's a little bit difficult to figure out where the center of it is. So let's see if we can use this information. It's all well and good. So this is the infrared spectrum of a molecule. And the question has called out to you 3 specific wave numbers and asks you to identify what's going on here. What do those 3 wave numbers or those 3 peaks in the IR spectrum indicate is present in the molecule? I'm going to send the link for the slides one more time. So I'm looking at 2950 right here, and I'm going to ask you, do you know what kind of peak this is? I'm looking at 1760, and I'm wondering if we know what kind of peak this is, and I'm looking at about 1200. Now, there are a lot of other peaks here that aren't called out, but I'm hoping that you will agree that the 2950, as Chantal said, is not super broad. It falls into the range of the CH, and so it is likely evidence of a CH. I hope you're looking at the 1760 and you're saying, well, it's close to the 1700 to 1750 range of a carbonyl. And I'm going to assume that that's correct. The values that are in the data booklet are where it is usually found, but it need not always be found in this tight of a region. So let's say 85% of the time it's here, but that means in our molecule, it might be just outside the region. So you need to have a little bit of room for it to be slightly outside the ranges that are given. And finally, I see a lot of you are indicating that the 1200 is more than likely evidence of a C single bond O. So this molecule has a C single bond O, a C double bond O, and an OH. I said OH and I'm losing my mind. I'm sorry. It has a C single bond O, a C double bond O, and a CH, a skinny peak over at 3000. I'm so sorry. And so my question for you is, what functional group do you think is likely? And I can see that Azan has already come up with an idea. If you have a C single bond O, a C double bond O, and a CH, but perhaps no OH, there was no super broad spectrum there, what is the most likely functional group? I'm going to give you a couple more minutes to answer that. Hey, you guys are doing fantastic. I'm so glad that you think that this is probably an ester. Now, it doesn't have to be an ester. It could be a ketone and an ether, or an aldehyde and an ether. But we are going to try to use the simplest possible guess, which is putting those two, C double bond O and C single bond O, together into an ester as our first pass at understanding the structure. And so I looked up a bunch of esters. This is all from the NIST website. And I found the IR spectrum of these 4 esters that all have the same empirical formula that we found at the very beginning of this, C2H4O. So can IR tell the difference between these structural isomers? No. So we've done sort of 2 experiments. In the first experiment, we figured out the empirical formula. In the second experiment, we took an IR spectrum and we found evidence that there was no OH, but there was a C double bond O and a C single bond O. So we deduced that it was likely that there was an ester. Because esters contain 2 oxygens, I went ahead and guessed that the molecular formula was going to be C4H8O2. And I drew out the esters that had that formula, and I thought of 4 of them. I then went back in and found their IRs, and I was a little bit nervous because all of them seemed so similar to me. And so infrared spectroscopy is a fantastic way of identifying bonds that are present and bonds that may not be present. But it is not a way of discriminating between or among those 4 different structures. We're going to have to know a little bit more about the molecule. So thankfully, there are a few more tools that we can use to figure out what's going on. So in each of these molecules, around 3000, you see a super skinny peak that we associate with a CH bond. We see this big, strong peak around 1700 that we associate with the carbonyl. And then over here, we see the CO single bond peaking out, but around the same value, I hope that you see a whole lot of weird structure. This structure is known as the fingerprint region. The fingerprint region works like your fingerprints. If I have your fingerprints on file, I can match them. But if you just sent me a copy of your fingerprint, there's no way I could know what you looked like. It works the same here. If we had a file that showed something that matched this structure over around 1000, we could say, why, of course, this is the right molecule. But we can't look at this structure and say, it's obvious that this structure corresponds to this molecule. So that's why it's called a fingerprint region. So that's where all of the CC information is. And there are just so many carbon-carbon bonds in slightly different contexts that it's a bit of a mess. And so we can use it to match two spectra, but we can't use it to identify a molecule. There is no specific exact range for the fingerprint region. It's going to be around 1,000, but it's just that whole rightmost side of the spectrum. So the C single bond O sometimes will stick its head out, and the C double bond O and the CC double bond will both be to the left of it. I got a good question from Azan. He was talking about if we had to describe the actual methods. Like, are they going to ask me how IR spectroscopy works or how NMR spectroscopy works? And since they got rid of the analytical option, they haven't actually asked about the instrumentation. This is really about a black box. We put molecules in one side and out comes this most beautiful spectrum that we can use. And so we need to be able to identify what's shown to us in the image, but we do not need to be able to really talk about the details of producing it. There are no questions that pertain to this fingerprint region. I just don't want you to be nervous about all of the peaks over here and how they do seem to be different. So there is some information in that, but like your fingerprint, it's hard for me to use that information to deduce what your structure might be. So knowing that it exists is the extent of the question that I would expect. The third technique is mass spectrometry. And so I did throw up a really old picture of what that looks like, just to remind you how the data might appear. So in mass spectrometry, what we do is we take your molecule and we get it into the gas phase and we shoot it with an electron gun. And the electron gun actually ejects an electron from the molecule, making it a positively charged molecule. And that positively charged molecule breaks apart into fragments. And those fragments will then move through the instrument by being accelerated by an electric field because of their positive charge, and by being curved or deflected by a magnetic field also because of their charge. And so we find that molecules that have a lot of mass are really hard to curve. But molecules that have a lot of charge, or fragments that have a lot of charge, are really easy to curve. And so if we look at how curved a molecule or a fragment ion is, what we'll find is some sort of a ratio of its mass and its charge. And so the axis of the horizontal axis in a mass spectrum is going to be called the mass to charge ratio. In topic 11 or 21, however you want to count this, almost always the charge is +1. That is to say that organic chemists and have really gotten extremely good at developing this method so that they only remove one electron, and they've done it really cleverly. Sometimes when you talk about mass spectroscopy in topic 2, when you're looking at chlorine and you realize that it exists as 2 different isotopes, I have seen a question where the charge was not 1, but was instead 2. So for us today, the charge is going to be +1, and that mass to charge ratio could just be the mass. But do be aware that I'm going to refer to it as the mass to charge ratio, just so you're ready for anything that comes up in topic 2. So if you look at the bottom of my screen, you'll see m/z is my x-axis. That stands for mass divided by charge. And here in organic chemistry world, the charge is just going to be 1. So this is a mass spectrum of the molecule that we've been working on. So you might recall the first thing we did was we found its empirical formula. The next thing we did was we looked at its IR spectrum, and we became relatively confident that it was probably an ester, but we weren't able to tell which ester it might be. And so now we've taken that same molecule, we've put it into we've taken its mass spectrum, and we have some data about it. On the x-axis, I am showing you the mass of the different fragments it fell into, and on the y-axis, I'm showing you the intensity. In my experience, we will not use the intensity. Instead, what we will use is the fact that specific signals are labeled in the question statement. That's how we're going to know where to put our attention. So you might notice that there are a lot of signals that I did not note, and that's because we're not going to fully understand the complicated chemistry that goes on in the mass spectrum. We are going to be able to find the fragments that we need to understand the molecular geometry of our problem. So here we go. Here's our mass spectrum. And perhaps the first thing we should notice is on the far right side, we have the biggest mass. The biggest mass with a appreciable intensity is 88. You'll see there's a tiny little one here at 89, and together we're going to figure out what that is. But first, what I'd like to do is I'd like to focus on the 88. This is called the parent ion peak, or the molecular ion peak. If I look at the empirical formula and I look at the mass of the molecular ion, what I can do is determine the molecular formula. That is, I could finally be confident that this is going to be a C4H8O2. I made that guess when you guys told me that you thought you saw an ester, but now I'm going to be confident. And the way I'm going to do that is I'm going to go ahead and I am going to deduce the molar mass of the empirical formula. So I took 2 times 12 for the 2 carbons, 4 times 1 for the hydrogen, and 16 more for the oxygen, and found that the empirical formula had a mass of 44. The molecule has a mass of 88. That means 88 divided by 44 is 2, or that there are 2 units of C2H4O in my molecule. Or I could multiply all of those subscripts through by 2 and say that my molecule's formula is C4H8O2. If the question that you're asked is, hey, what's the molecule? The answer is C4H8O2. If, however, and this is really important, it's been worth a mark every year, if the question that is asked is, what is responsible for the peak at 88? Your answer must include that positive charge. So we can take the empirical formula and figure out the molecular formula by looking at the peak that is farthest to the right and of appreciable size. We compare the mass of the empirical formula to the mass that we read in the mass spectrum by dividing them. 88 divided by 44 was 2. And so we multiplied our empirical formula through by 2 to figure out our molecular formula. The identity of the peak to go through the mass spectrum must include a plus. It had to be accelerated by the electric field, and it had to be deflected by the magnetic field. Both of those steps required my thing to be charged. So every year there are questions about, hey, what's that peak at 59? And if you don't put the plus sign, you will lose the mark, even if you know what it is. There is always a positive charge. The parent peak is the peak farthest to the right, and the positive charge comes from the way the mass spectrometer works. The mass spectrometer starts with first vaporizing our molecule and then shooting it with an electron gun. And what the electron gun does is it actually scatters electrons off of your molecule. Your molecule is in a really high energy state. It's got a positive charge, and it like falls apart into different fragments. And then we see the fragments come out the other end and make these peaks. And we're going to use the sizes of those fragments to understand the shape of this molecule. I'm getting a lot of questions about the 89 right now, and Dong just answered it. He said that the 89 is because of the natural abundance of isotopes of carbon and hydrogen. So if you think about the molar mass of carbon, it's 12.011. That's because there's not a whole lot of carbon-13 in this world, but there is about 1%. Similarly, there's not a whole lot of deuterium in this world, but some hydrogen is deuterium. The molar mass is 1.00794. There's a little bit. By the time that you have 12, that is 4 carbons and 8 hydrogens, of those atoms put together, the probability becomes a little bit significant that you'll have at least one of those heavier isotopes. And so you'll start to see this peak build in. It's called the M+1 peak. And it's because of, again, the natural abundance of isotopes. So we'll see that in a few slides, but it was just pervasive enough in the questions and you guys were answering each other that I wanted to make sure that we talked about it when it was important to you. So the 89 peak is called the M+1 peak, and it's due to the natural abundance of isotopes of carbon and hydrogen. I am more interested right now in what's going on to the left. What are these fragments that I'm seeing and where are they coming from? In the data booklet, the information that is given to us is the fragment that could be lost and its mass. So fragments are neutral. We imagine that we had this positively charged ion with a lot of energy in it that broke apart, but that positive piece, the positive fragment, is the only one that I will be able to see in the mass spectrum, because that's the only one that will be accelerated and deflected. So as I've been trying to say, everything here will have a positive charge. And so the piece that fell off must be neutral. And so in the data booklet, everything they show you is neutral because those are the pieces that got lost. So I'm just going to do some arithmetic. And the arithmetic is going to look like, oh my God. Okay. I'm going to do my arithmetic and maybe we'll go back and do that question. I apologize. I'm going to do my arithmetic, and my arithmetic is going to start at this parent peak. It's going to start at the 88. It's not going to look at that little tiny M+1 peak. It's going to look at the real parent peak, the 88. And I'm going to subtract the peaks that I see immediately to its left. So I took 88, I subtracted 59, and I said I lost 29 mass units. Or I took 88, I subtracted 57, I lost 31 mass units. In the data booklet, I can then see that a loss of 31 is a loss of a methoxy. A loss of a 29 is a loss of an ethyl, or what I call a CHO, or an aldehyde. So what might that look like? Well, I'm going to take the parent peak. I'm going to lose those fragments that I took from the data booklet, and now I'm going to subtract. And so what I mean by subtract is I used to have 4 carbons. One of them is going to go away, so I'll have 3 carbons. I used to have 8 hydrogens. 3 of them are going to go away. Now I have 5. I used to have 2 oxygens. One of them is going to go away. I'll only have 1. So this peak, this 57 peak, is going to be C3H5O plus. And this peak, I'm not sure what it is. I'm either losing an ethyl or an aldehyde. And so I just subtracted both to see what that structure might look like. Oh my God, everything is broken. And so I wrote those values down. So I hope you see that we took C4H8O2 and we subtracted CH3O, and that's the C3H5O plus I promised you. Similarly, I subtracted C, H, and O from this molecule to get C3H7O plus. That's the top choice. And then in a separate step, I subtracted C2H5 to get C2H3O2 plus. So I wanted to give you a chance to do it, but I wanted to finish my work first. So I'm going to go back. And you can pretend you didn't see that. If you're in the Menti, you can answer the question. If you're not in the Menti, you can throw your answer in the chat. I have compound X. It has a molar mass of 148. In the spectrum, I see a peak at 117. All right, look at that. So you guys did a great job answering. Let me make sure that you guys can hear me. I'm just going to go to the chat if you can. Okay, Susanna's making me think that we have success. I'm so sorry. The mass loss table is absolutely in the data booklet, Chantal. Yes. And I think it's misleading because it doesn't have those little tiny plus signs. And I so wish they were there because we would just get so many more marks. And then Arnav, you asked me a great question in the question and answer. Feel free to use that. The question was, how do we know where to start counting the fragments, essentially? And the answer is we start from those parent peaks. We start from the rightmost peak. That's going to be the peak at 88. Thank you, Galena. Yes, it's table 28. It's really important, go back to Arnav's question, that you don't try to do this serially. That is, you don't go to 59 and then subtract 2 more to get to 57. You'll find nothing helpful that way. We're always going to start from 2 places. One place is going to be that parent ion, 88. The other place is actually going to be 0. We can use that same fragment lost table to figure out the fragments that we do have. And so starting at 0, do you see my peak at 15? That's the presence of a methyl. Starting at 0, is it not good, the voice? Super nervous, like everything crashed. So if my voice is, okay. If we start at 0 and we get to 29, that's the presence of a aldehyde or an ethyl peak. So I'm never going to start at 57 and subtract more. I'm only going to start at the parent ion or at the 0. Those are the only 2 places I'm going to go. So we have identified 3 of these peaks. The parent peak, the 59, we're not too sure which one of these it is. And the 57, we're at 100%. We know it's the C3H5O+. For the 15 and the 29, I'm trying to talk you into knowing what they are, saying that we can use that same table 28, the fragment lost, to predict that those are fragments found. And so now we've come up with the identity of what each of the peaks most likely is. I promised you I would talk about that M+1 peak a little bit later. You can see here in my slides, that's where I included that M+1 peak, but you have already answered that question for each other, saying that that's the presence of naturally occurring isotopes of carbon and hydrogen. So if we put these 2 pieces of data together, on the right-hand side, I have the IR spectrum, and on the left-hand side, I have the mass spectrum. You can actually figure out what the molecule has to be. So we believe that it is a molecule that has the structure C4H8O2 because we know its molar mass is 88. We believe that there's an ester because we found evidence of a carbon double bond oxygen and a carbon single bond oxygen in the IR spectrum. We also knew it wasn't a carboxylic acid because there was no evidence of an OH bond. When we looked at the fragments, probably the most telling fragment was the CH3O, or the methoxy fragment. That loss of 31, that is 88 minus 57, means that somewhere in this structure, I needed to find a CH3O. And so I drew a CH3O on the right-hand side of my ester. So there's the COOC that I associate with an ester, but I put the methyl so that I could lose 31, a fragment of 31. Then I needed to be able to lose a fragment of 29. And I told you I wasn't sure if that was a CHO or an ethyl group. But look, if I were to put an ethyl, that would account for the other 2 carbons I'm missing. I needed to have 4 carbons, and it would turn this molecule into something that's quite reasonable, methyl propanoate. You can see the presence of a methyl fragment right here on the right. So that's why we have a peak at 15. You could see the presence of an ethyl fragment right here at 29. That's why we have a peak. You could see the ability to lose the methoxy fragment. That's why we lost 31. And you can see the ability to lose an ethyl fragment. That's why we lost 29. You do not need to worry about why it is possible to lose the CH3O, but we don't find the CH3O. There's not a big peak at 31. That's beyond the scope of our syllabus. Absolutely, the fragments lost are neutral. However, a CH3 plus fragment could be found. So in the data booklet, they just talk about losses. In the actual mass spectrum, we talk about what we find. So we have to put a plus sign on everything. But we can use those same mass values. The peaks over on the left, we didn't need to use because we had deduced together that the loss of the CH3O kind of informed what the structure had to be. But that is free information over there, that we have a methyl and an ethyl. And knowing that that ethyl was likely to be here was useful. In a typical question, they would ask you to identify what was going on, or the molecular ion, with a mass to charge ratio of 57. And so in a typical actual exam question, they would just show you this mass spectrum. Underneath it say, what's responsible for the signal at 57? And you would write down C3H5O+. It is typically later in the problem that you're going to have to deduce the full structural formula, and you're often not going to have to show how you came to it. You're going to iterate toward it. We used the IR data to figure out it was an ester. We used the empirical formula data to figure out that its molecular formula, along with this parent ion peak, was C4H8O2. So we're using a lot of different pieces of data to draw our structure. So I just wanted to show you that the peaks on the left can be helpful, and maybe they will be. So Vanessa, you said it great. The fragment that is lost is neutral, but the thing that is left is an ion. You can refer to the diagram as a graph if you want. I would refer to it as a spectrum, Elizabeth. So I wanted to work through one of these questions with you because I feel like I've been talking a lot. And I thought maybe we could change it up for a minute. And so I put together some data, and I would like to figure out what this molecule is. So the first piece of data that I've given you is the mass percentages of carbon, hydrogen, and oxygen. And so the first thing that you're going to need to do is to figure out what the empirical formula is for this material. So I'm going to give you a minute. I'm going to answer a few more chat questions, and then we're going to solve that together. What I hope that we did, and I'm just going to try to write out for you, is that I hope you said you have comedy of errors. I hope you said that you have 69 point. Oh my goodness, you're never going to believe that my iPad pencil just broke, just for kicks. Don't worry, I have another nib. All right, so I hope you're going to say that you have 69.7 grams of carbon, and you're going to divide that by its molar mass to identify how many moles of carbon that you have. I got 5.81. I hope you're going to say that you had 11.7 grams of hydrogen. You're going to divide that by its molar mass to say you had 1.01. And I hope that you said you had 18.6 grams of oxygen, and you're going to divide that by its molar mass in order to say that you had 1.16 moles of oxygen. I'm going to divide each of these through by the smallest number. That's the moles of oxygen. And I got a ratio of 5 to 10 to 1, or a formula C5H. That's an H, everybody. H10O. Are we good with that? Cool. So let's move on to this problem. One more time, we started with the empirical formula. And we got it right. The next thing we're going to do is we're going to try to state the molecular formula given that in the mass spectrum, that parent peak is at 86 for its mass to charge ratio. So I'm just going to write down the empirical formula that you already had and give you a second to think about this. And then we can practice calculating the index of hydrogen deficiency. I feel like that was that area that maybe I could have done a better job explaining. Okay, many of you are saying it's the same thing, and I agree. 5 times 12, 10 times 1, and 16 is going to give me a total of 86 grams per mole as the molar mass of my empirical formula. I'm going to take the 86 that I read in the mass spectrum. I'm going to divide it by the 86 of my empirical formula. So on top, I have the molecule. On the bottom, I have the empirical formula. I get 1. And so, of course, the molecular formula is exactly the same. Now, the index of hydrogen deficiency, what we're supposed to do is we're supposed to write down a formula that looks like the index of hydrogen deficiency is equal to 2 times the number of carbons plus 2 minus the number of hydrogens minus the number of halogens plus the number of nitrogens all over 2. And here we can be pleased that we do not have any halogens and we do not have any nitrogen. Oxygen doesn't appear in the formula, so I just ignore the oxygen. So the IHD is going to be equal to 2 times the number of carbons plus 2 minus the number of hydrogens divided by 2. And that number is 1. There is 1 double bond or 1 ring in this compound. Good? I don't believe that you're ever going to be asked to show your work for the IHD. I believe more often than not, it is just a calculation that's in a multiple choice question. So you're just going to have to circle the right answer. Azan, I'm not sure what your question is. So if you want to clarify it, that's cool. And if not, that's cool too. The infrared spectrum was obtained for this molecule, and we're going to use section 26 of our data booklet to come up with 2 possible molecular structures. And so I'm looking at this spectrum, and I'm looking at my data booklet, section 26, and I'm trying to see what information I have. So on the right-hand side, you see that fingerprint, and I'm not able to resolve anything over there. So if I had a book that showed every IR spectrum that had ever been taken, I could probably do some matching. But other than that, there's nothing useful for me. There's only 2 useful things here for me. This peak right here appears to be at 1700. So if this is 1500 and this is 2000, 1750 would be right there. It seems to be just shy of 1750. And so in my data booklet, I found that there are peaks between 1700 and 1750 that I associate with the carbonyl stretch. And so I believe my molecule is going to have a carbonyl. I also believe that I can see some evidence of structure in this peak at 3000. And so when I have peaks on the left, I've always got to decide if this is a CH or if this is an OH, because I can see those little ripples of structure, but maybe more because I know the empirical and molecular formula of this compound is C5H10O. I'm going to say, of course, this is a CH bond. And I'm going to tell you a truth here. The Menti is not on right this minute. I have you on my laptop, on my iPad, so that I can write on the screen. We'll go back to the Menti in a minute, but it's not moving right now. Only the Zoom is moving. We'll get back to it as soon as we're done with this problem. So what I'm trying to admit to you is that sometimes I will leave the peak over at 3000 blank until I look at some of the other information in the problem. And when I do look at that other information in the problem, that's when I can be confident that I have an OH. I realize I can advance the Menti for you. So I apologize, Urim, I'm on it. There you go. So now you should see the same thing on both screens. You're welcome. I just didn't think to do it, but I'm on it. So we have this molecule. We believe it has a CH. We believe it has a C double bond O. So we believe it's going to be a ketone or an aldehyde. We're not sure which. And so in question E, we're asked, explain why the infrared spectrum alone is not useful in confirming the identity of this molecule. And the reason for that is because all we can see evidence of is the presence of a C double bond O and a CH. So we know those are the important bonds that are present in our molecule, but we don't know how they're arranged. So I drew a ketone and an aldehyde as examples, but it would definitely be a whole host of molecules. Like we could probably draw 10 more if that was the game we wanted to play. So I and everyone I've ever worked with finds it difficult to decide if this is a broad peak or not. So I'm trying to show you the little ripples on the bottom as evidence that it could be a structured or not broad peak. An OH peak is going to be bigger and usually slightly further to the left. So I'm trying to draw it smooth. I'm trying not to have any, I'm trying to draw like a big, fat, smooth curve. Sometimes you will see a little action over here where you can see some CHs poking out. Because I find that so difficult, I decided to second guess myself and I went back to the structure of this molecule. We knew that the molecular formula was C5H10O. We had already accounted for the oxygen. We know that the oxygen is in this carbonyl bond right here. There's no doubt in my mind that that's a C double bond O. If the oxygen is in a carbonyl, it can't also be in an alcohol or a hydroxy group. So yes, so if I'm looking for evidence of an OH, I'm looking for a much wider curve, and they are generally a little bit smoother, though sometimes you can see some stuff poking out of them because the CH peaks are underneath. All of us find it difficult to decide if something is broad or not in the absence of things to compare it to. That's why I showed you the structure of the propane so you could get perhaps a beginning of a sense of what the different shapes looked like, because the word broad is perhaps not unique or significant enough for us to know exactly what they have in mind. So if you go back a few slides, or if you look at this again, feel free to check that slide out and just have a mental image of what the OH more smooth broad curve looks like. I can absolutely try to send the PowerPoint again. I believe that's going to be it. All right, we did a problem. So that would be more like a paper 2 question on this. Hope it was helpful. Not sure this is the moment, but there is a feedback form you can fill out. I'll have this QR code a few times throughout. It's just a Google form so that I can do a better job when I do this again, or you can tell me what you really enjoyed so I can continue to incorporate that. So please do me a solid and fill it out. And again, that will come up again. The third type of spectroscopy is definitely the most important and the most interesting and the most marvelous. It's called nuclear magnetic resonance spectroscopy, or NMR spectroscopy, or proton NMR spectroscopy. And it has to do with having charged particles with spin. So you know from electron configuration that electrons have spin. And we talk about Hund's rule says we have to maximize the number of electrons that are spin parallel. Yes, Pauli exclusion principle, all that stuff. What they don't tell you is that protons have spin. We as chemists don't think about protons a whole lot, or the structure inside the nucleus, but there's a whole lot of stuff going on in there. And so what's going to be important to us today is just the fact that protons have spin. And particles that have spin are affected by magnetic fields. They behave like little tiny magnets. And if that particle is aligned with a magnetic field, it will be in a lower energy state. And if it is aligned against that magnetic field, it will be in a higher energy state. And so we can use light to change the orientation of that spin from aligned with to aligned against and see how much energy that costs us, see where it absorbs light. And we can actually deduce the structure of organic molecules and huge proteins using this trick. So Marco, we're going to be talking about NMR for the rest of this. X-ray crystallography has not been something that a lot of questions have been asked about. Traditionally, it's just been a single multiple choice question, assessing your understanding of using X-ray diffraction as a means of taking like a snapshot of a picture using light that's on the same wavelength as the distances in a molecule. And so it's a way of determining the length and angles of bonds. Chantal, we'll go over it again in a second. We'll see the things, the magnets pointing with and against the field. I'm going to show you an NMR spectrum and just try to imagine what it is we need to understand. So an NMR spectrum looks like this for chloroform or trichloromethane. And so I find them a little bit bewildering because one more time, the x-axis runs in the direction you wouldn't suspect. The small value 0 is on the right and the big value 11 is on the left. And the units are parts per million. And then the y-axis is intensity. And so here you can see that in trichloromethane with only a single hydrogen atom, so that single proton in the hydrogen atom is the one that I'm going to be questioning in my instrument. And I am watching the alignment of that particular proton go from being with an applied magnetic field to against it. That's all I'm seeing. There's one energy that corresponds to flipping that spin, and it's right there. And on my graph, it seems to show up at 7. And so I want you to ask yourself, like, why is it at 7? Why isn't it 0? Why isn't it at -5? Or how do I make it taller? Or why don't I see the carbon in the chlorine? And what the heck is a part per million? Like, there's a lot here. But as we discussed, we're not responsible for the technique. We're just responsible for understanding the spectrum that comes out. So we're not going to have an encyclopedic knowledge of how to change all of these things, but I think you'll have a pretty good idea of what they mean. So first, we can focus on just the hydrogen atoms because hydrogen is pretty special in just having that one proton in its nucleus. And so there's a net spin in the nucleus, and that's why we can see it. Carbon-12 doesn't have a net spin, and so it's silent. But if you take an organic chemistry class in your future, you will see that carbon-13 NMR is another really powerful technique. And if you're interested in biology, they can look at phosphorus nucleuses to look at the phosphate backbone of DNA. Like, there are lots of cool techniques, but we're just going to look in the right part of the spectrum for hydrogen because every organic molecule has hydrogen, and it's a rich way of understanding the structure. The way that we're going to shift left and right is we're going to change the chemical environment. And to change the chemical environment, what we're actually doing is we are changing the number of electrons that are near our proton. So in the presence of the magnetic field, what happens is that the electrons will naturally start moving in such a way as to decrease the applied field. So if you're a nucleus that's really, really close to a whole lot of electrons, if you sort of have all of the electrons you expect, would be another way of saying that, you're going to feel a smaller magnetic field, and it's going to take less energy to flip you. If, on the other hand, you're near something really electronegative, and so all of your electrons have been pulled away from you, you're going to be sitting out there feeling the full force of that applied field, and it's going to take more energy to flip your spin because you feel a stronger magnet that you're trying to align with or against. And so that is like a really long-winded and probably too technical way of saying that what we're doing is we're going to see that hydrogens in different chemical environments a hydrogen that's near a chlorine, a hydrogen that's near a double bond. They'll have slightly different amounts of electron nearby, amounts you don't have to measure, you just have to believe they're different. And because of those differences, they're going to appear at different places in our NMR. So we refer to that as their chemical environment. Hydrogens that are symmetrically different. So I can't like take the molecule and flip it and say, oh, that's the same. Or I don't have three hydrogens on the same carbon and say, well, that carbon is just freely rotating in that molecule. And all of those hydrogens are just doing exactly the same thing. So they're equivalent. All hydrogens that are not really, really equivalent are in slightly different chemical environments. And so they will appear at different places in the spectrum. To start the spectrum, that zero on the right-hand side, we use a molecule called tetramethylsilane, or TMS. And I drew it for you at the bottom. It's a silicon, and it's got 4 methyls, tetramethylsilane. Now, what's interesting is silicon is less electronegative than carbon. And so that carbon, each of those 4 carbons, is going to feel like a little extra electron density because it's going to pull a little bit harder on that bond because the silicon carbon bond is just a little bit polar. And that's going to push more electrons toward the hydrogen. So the hydrogens in tetramethylsilane are just a little bit more shielded from that magnetic field. That is to say, they feel it less. And because they feel it less, it takes less energy to flip them around. And it takes less energy to flip them around than it does any molecule that we're going to study in organic chemistry. So the hydrogens in this molecule, if you add it to your sample, are going to show up just to the right of all of the hydrogens that you care about. And so it's a great internal standard because it's out of the way and it's chemically inert. There's also 12 hydrogens of the same type in that molecule. And that means even if you add a relatively small amount, it will have a pretty big peak. And so TMS, or tetramethylsilane, is going to be my zero. It's going to be a chemical shift of 0. And everything else is going to appear to the left of it. It's going to be less shielded and more shifted to higher parts per million. So Dong, everything you said is right, except for the lower parts per million should be higher parts per million. If you have less shielding, you're going to be more shifted. And when we shift you to the left, which is a bigger number on our scale. And maybe you can see that. This is a table from your data booklet, just sort of re-engineered to point out maybe a few things. It's in the same order. But here you have a hydrogen that's in a methyl group, and we expect its shift to be quite modest. This is a very shielded hydrogen. It's not near anything particularly electronegative, so it should have most of the electrons it came with. And so it's going to be pretty close to that tetramethylsilane. If, on the other hand, we were to look at this hydrogen in carboxylic acid, we can only see the Menzi. How's this? If instead, I'm going to fix that. Feel free to scream when something's not working right. Like I'm extremely happy to just fix it as soon as I notice. Is that good still? I apologize. Like I just didn't realize it. It looks good on my screen, so I just was going. But like I'm doing my best to read the chat. So if you notice something that's not going right, just say so, and as fast as I can, I will try to fix it. So I'm looking at the carboxylic acid here. This hydrogen is next to 2 oxygens. Those oxygens are going to suck away all of the electrons, and that hydrogen is going to feel the full force of my magnetic field. So it's going to be very shifted. These numbers are given to you. You don't have to predict anything, but different chemical environments, largely related to how much electron density is around that hydrogen center, are going to produce peaks at different locations along my x-axis. So parts per million is a strange way of measuring it. I'll be the first to agree. But we have a table that relates each type of hydrogen to where we might expect to find it. No worries. Just to show you that a little bit differently, I took 3 molecules. I took chloroethane, bromoethane, and iodoethane. And I'd like you to notice a couple things. First, I'd like you to notice that the shift increases as we go to the left, and that the most shifted peak is in this top spectrum that's associated with the chloroethane. Chlorine is the most electronegative of my elements. It's going to remove the most electron density, and that's why it's going to be farthest to the left. But you can see that effect isn't huge. I also want you to notice that there are 2 peaks here. That means that there are 2 different chemical environments. You can be a hydrogen that's attached to a carbon that's got a chlorine on it, or you can be a hydrogen that's attached to a carbon that doesn't have a chlorine on it. There are 3 hydrogens of that first type and only 2 hydrogens of the second type. This peak is taller than this peak. The intensity or the height of the peak or the area underneath the curve is proportional to the number of hydrogens of that type. So the location has to do with the chemical environment. The number of locations has to do with the number of chemical environments. And the height has to do with the number of hydrogens in that environment. There are a few different ways that you can measure the height. One way is you can just eyeball it and say it's taller and hope that's good enough. In this case, it is kind of good enough because we have a 3 and a 2. Sometimes you can use a ruler if the peaks are all kind of skinny, but sometimes they'll actually draw a little integral sign on the curve. And when they draw that little integral sign, you're meant to get out your ruler and measure the height of the integral to deduce the relative area under that curve. So you 100% want to bring a ruler with you to this exam. You can use it in NMR to figure out the relative number of hydrogens in different chemical environments. You can also use it for chromatography if you're doing option B to measure the retention factor of different spots. There are a few places where it's handy. So we have a better idea just looking at these 3 curves about what the NMR is all about. It's going to show us again the number of chemical environments, the number of hydrogens in each of those environments, and eventually it's going to tell us what's next to what, but we're going to have to wait a second to get there. So if you're in my Menti, this cleverly doesn't have a link to it. I wondered if you could help count how many chemical environments are present in this molecule. And if you're not in the Menti, no worries. You can throw it in the chat or just think to yourself what you think it is. That certainly didn't work quite the way I envisioned. Okay, we seem to be normalizing around 3. Around 4. Thank you, Dong. Menti is just a way for people to do a little bit of live answering to make this a little bit more interactive. It's hard to sit and listen for this long without doing anything. Oh, you guys are making me a normal distribution. I love it. So it seems to be that many of you think that the answer is 4, that there are 4 chemical environments here. And if we were to count them together, you're going to have a methyl group on the left and a methyl group on the right that are each 1 carbon away from this central carbon. Okay. Then you're going to have hydrogen down, and you're going to have a hydrogen on this hydroxyl. To my count, the 2 methyl groups appear to be equivalent to each other. The methyl groups are attached to the same carbon. So the 3 hydrogens on the methyl are the same, and the two methyls are the same. So we actually have 6 hydrogens of that type. We have a single hydrogen of this central type right above the 2, and we have a single hydrogen of this hydroxyl type. So I hope you'll agree with Linda that the answer is 3. There are 3 different chemical environments in this molecule. We would expect to see 3 peaks in this molecule. Why my next page says 4 is, like, honestly anyone's guess. Way to go and think for yourselves. Vanessa, I'm going to do my best to count again. So we're going to fix my slides. So you guys can also scream at me if you think I'm wrong, or say it really nicely. I can take both. So here we go. I'm looking at structure 2, and I'm trying to count the unique types of hydrogen. And if I'm looking at the unique types of hydrogen, my feeling is that this methyl and this methyl are the same. And because those 2 methyls are the same, that is to say they are attached to the same central carbon, the 3 hydrogens here and the 3 hydrogens here should be the same. So there should in fact be 6 hydrogens of that type. Then there should be 1 hydrogen of this type. There is no other hydrogen on that secondary carbon. And of course, this hydrogen on the hydroxyl is its own type. So contrary to what my garbage slide says, I feel relatively confident that there are 3 hydrogen environments and they're in a ratio of 6 to 1 to 1. Let's try another one, just because I feel like I did you wrong and I don't want that. We're looking at structure 3 just for a second, and we're going to try to figure out how many unique chemical environments there are. So I don't have a fun way for you to answer other than the chat. Kotaro is saying that, as many of you are, that we think the answer is going to be 3. There is a methyl group on the left-hand side. All of the hydrogens on that same carbon are equivalent to each other, and they are of 1 type. They are different from the methyl group on the other side because these are adjacent to the O, whereas these are not. So they are not equivalent because they are in different positions. Finally, that methylene carbon has 2 hydrogens of 1 type. Hydrogens on the same carbon will always be equivalent, but there is no other carbon that's attached to a methyl and an oxygen. So there are 3 environments and a 3 to 2 to 3 ratio, as a few of you are saying. We check out this first one just to practice this one more time. I hope that you're going to agree that this methyl group is 1 type. This methylene that is next to the methyl is different from this methylene that is not next to the methyl. I could describe them differently. And finally, this hydroxyl is a 4th type. So I hope you will agree that there are 4 different chemical environments here with intensities 3 to 2 to 2 to 1. And so if we were to look at the NMR spectrum of these 3 isomers of propan-1-ol, we could actually just look at the number of peaks and the heights of the peaks to figure out which molecule we were looking at. Structure 1 would have 4 peaks. Structures 2 and 3 would each have 3 peaks. However, the intensities would be different. This one is going to have 1 very tall peak and 2 little tiny short ones, whereas this is going to have 3 peaks of more even size. So we are counting the number of unique chemical environments and the number of hydrogens in them. And we are burning the rest of this slide. Okay, I feel like you guys are answering each other's questions. So Zach, I told you that the two CH2s were different because one is next to a methyl and one is not next to that methyl. So I could differentiate by describing where they are in the molecule. And because I can say that difference, I know that they are not equivalent. We'll be in the HR part in just a sorry, the HL part in a second. We can go faster if we need to and burn that. We just practiced this. We were looking at the ratios of the peaks and the IHD. We're told that the ratio here is 3:2 and that the IHD is 2. And we're trying to figure out if we can deduce which compound it is. Since the IHD is 2, there have to be 2 pi bonds or a ring and a bond or 2 rings. And so I believe that you will agree that only B and D are reasonable options. Furthermore, the ratio of the types of hydrogens are 3:2. If I look at option B, my expectation is that I would have 3:2:2:3 for different chemical environments. Whereas if I were to look at option D, there is a mirror plane that goes down the center of this molecule. And so there are actually 6 of the methyl type hydrogens and 4 of those methylene type hydrogens, or a true 3:2 ratio, only 2 types of things. So those of you who answered in the Menti, that's cool. I know I'm not showing it right now, but I agree with you that the answer is going to be D because it supports both the ratio 3:2 and the IHD of 2. I wanted to point this out just for a moment. We were talking about those integral signs. And you can see that there are some integral signs that are drawn above the curves. And so when I was saying bring a ruler, what I'm asking you to do is bring a ruler so you can measure from the top of this integral sign to the bottom of this integral sign and find out that it's 3 centimeters. And then you're going to measure from the top of this integral sign to the bottom of this integral sign and figure out that it is 2 centimeters. And the ratio of the lengths of those lines will be equal to the ratio of the number of hydrogen atoms. In this problem, we're told that there is 1 methyl group. I'm going to assume that's this peak right here. And so it's going to indicate to me that there are 5 chemical environments and that the 5 chemical environments have relative intensities 3:2:2:2 to this shorty little one right here, 1. So that is the integral sign that I was speaking of. And I hope that helped. There is some pressure to talk about splitting. So let's do it. There's just a couple more practice problems that we're not going to solve, but the answers and the questions are there. So feel free to do them on your own. This PDF will be here forever. So take your time when you have it and feel free to practice. Shahed, the point of the integral signs was to exactly measure the ratio of the number of hydrogen atoms. For spin coupling, that's the strictly HL part of this. What we're going to say is that the hydrogen atoms near you actually are going to behave like little magnets. And so the hydrogen atoms that are near you, that are different from you, are going to affect the magnetic field that you feel. And so you're actually going to find that you absorb a slightly different energy than you expected. And so if you look at the molecule dibromo-dichloroethane, it just has two hydrogens in it, and the two hydrogens are in different environments. The hydrogens are in different environments because one's adjacent to bromines and one's adjacent to chlorines. Since bromine is less electronegative than chlorine, these are the bromine guys and these are the chlorine guys. But when I look at that peak, that chemical environment, I see it's split into two. We refer to that splitting as a doublet. So anytime you have two peaks of the same size, we call it a doublet. And the reason that it's split into two is because when this hydrogen looks or feels the effect of the hydrogen over to its left, the hydrogen to its left can be aligned either with the magnetic fields or against the magnetic fields. If it's aligned with the magnetic field that our hydrogen feels will be slightly stronger. And so it will appear just a little bit to the left of where we thought it might be. But if the hydrogen next door is aligned against the field, then the field it experiences will be just a little bit smaller than we expected, and we will see this peak. And so the fact that the neighboring hydrogen, and by neighboring hydrogen, I mean one hydrogen that is 3 bonds away. So I am counting 1 bond, 2 bonds, 3 bonds away. That's where I'm looking to find the one that's going to affect me. When I look at that hydrogen, it can be either with or against, and so I will be split into 2 peaks. When the hydrogen on the left looks over to the hydrogen on the right, it's going to experience the same thing. That hydrogen also could be aligned with or against, so it too would be split into a doublet. If we had a slightly more complicated molecule, now we have 2 hydrogens on one carbon and 1 hydrogen on the other. We're going to see that the splitting pattern is just a little bit more complicated. For the hydrogens on the right, these are going to be the ones that appear less shifted on my graph. They're going to look over to the left and say their hydrogen 3 bonds away can be either spin up or spin down. So they will appear as a doublet with intensity 2 because there are 2 of them. On the other hand, the hydrogen on the left, this guy, is going to look to its right, and there are 2 hydrogens there. And because there are 2 hydrogens there, the 2 hydrogens both could be aligned with the field, or could be aligned with and against, or against and with, or both could be aligned against the field. There are 2 to the second power possibilities, but it gives us what we affectionately know as the n+1 rule. When there are 2 hydrogens that we are able to see 3 bonds away from us, what we will find is 3 peaks corresponding to the different ways that those 2 hydrogens can organize their spins. So if I see a splitting that shows up as a doublet, I'm going to know that there is 1 neighbor hydrogen. And if I see a peak that is split into a triplet, I'm going to know that there are 2 neighboring hydrogens. So n is the number of hydrogens, and the n+1 rule is just saying that the splitting will be into 1 more peak than the number of neighbors. So if we look at this for a minute, you're going to see a singlet. That's just a peak all by itself. You're going to see a quartet, and you're going to see a triplet. How am I figuring out those shapes? I am just counting the really thin peaks inside that chemical environment region. Now, if you look like a singlet, I could use the n+1 rule to say that you have no or 0 neighboring hydrogens. Now, the integral here is 3. So that means I have 3 hydrogens of one type but they have no neighbor. So whatever it is I put in that box cannot have a hydrogen on it. On the other hand, on the right-hand side, I have 3 carbons. Again, that's the integral sign of 3 that are shown as a triplet. So they have 2 neighbors. And I have 2 hydrogens, that's the integral sign, that have 3 neighbors. This pattern of a quartet next to a triplet is by far the most common pattern we see. And this is the symbol of I have an ethyl group. An ethyl group is going to have 3 hydrogens next to 2. So it's going to have an intensity of 3 and be split as a triplet, and 2 hydrogens next to 3. So an intensity of 2 and appear as a quartet. Now there cannot be a hydrogen on the other side of my CH2. Otherwise, the splitting would be more complicated. So our molecule, if you're looking at the multiple choice, is going to have an ethyl group on one side and a methyl group on the other. And in between, it's just going to have not a whole lot of stuff. By a whole lot of stuff, I mean hydrogen atoms. And here you can see that it's an ester functionality that we're using to not have any hydrogen atoms present. So I would suggest the answer has to be either A or B. To discriminate between A and B, you're going to have to go to the table of NMR values. In the table of NMR values, you're going to find that a hydrogen that is adjacent to the carbonyl side of an ester usually shows up with a shift around 2.5, while a hydrogen that is adjacent to the ether side of an ester is going to have a shift around 4. So if our singlet methyl group is closer to 2, it's going to be structure A. And if it's closer to 4, it's going to be structure B. So the best answer here is B. Now, could you do this without a data booklet? No. I do not believe that you were responsible for knowing the shifts of molecules of hydrogen atoms within your molecule without the presence of a data booklet. As we're changing the syllabus, I stole this from the new syllabus. They have the data booklet available to them. Because we're in a review session, we have the data booklet available to us. So I made it into a multiple choice question to try to help mentify it, but no one is going to expect you to know that the shift on one side of an ester is 2.5 and on the other side is 4. So please don't be concerned about that. The only thing that the HL has added to this is our discussion of TMS, or where 0 is on the graph, and the ability to know what kind of neighbors you have. So this N+1 rule. Now, there are a couple of provisos to that N+1 rule that are relatively important. The first one I wrote here. It says if there are 2 sets of adjacent hydrogens, things get complicated. Don't expect to be able to count them. We'll just call it a multiplet. So this is what I mean. If I had propane 1-all and I was looking at this set of hydrogens, this set of hydrogens would look to its right and say I have 3 neighbors, but it would look to its left and say it had 2 neighbors. And so you might be inclined to say there are 5 neighbors overall. Maybe it will show up as a sextet. Honestly, what happens is that it just looks a bit like a mess. It's hard to count to 6. And so often the word multiplet is used to try to distinguish that. The other thing that I would like you to make sure that you know is that OH is not split and will not split. It's because of hydrogen bonding in the solvent that you're running the NMR in, but this H will always appear as a singlet. Always. And even though we are 1, 2, 3 bonds away, this H will not be split by the OH. So the hydroxyl group behaves a little bit differently. It always appears as a singlet and does not split anything else. I know that's a little bit crazy. It's because of hydrogen bonding. So let's see if we can use our understanding of this complicated spectrum to solve a last problem. And maybe not that one. So the last problem that I'd like to do, because I think some of you think that we're done in 5 minutes, I'm happy to stay on for a few more if you have questions. But if you have places to go and people to see, just like to do this one last problem. We have a molecule that is 85.6% carbon. It is a hydrocarbon, so it only contains carbon and hydrogen. And I have put together all of the data. So we have the IR, we have the NMR, and we have the mass spectrum. And the question is, of course, what is this molecule? So I'm going to give you a minute to think about how you might approach it, and then we're going to try to do it together. I'm trying to get a calculator going so I don't look silly. All right, so in the interest of time, I tried to give you a minute to think about your plan of attack, but maybe you didn't get to fully flesh it out. The first thing I would consider doing is figuring out the empirical formula. I took 85.6 grams of carbon. I divided by the molar mass to get the moles of carbon. I got something just over 7. I took 100 minus 85.6. I got something just over 14. I divided that by the molar mass of hydrogen to figure out that I had about 14.2 moles of hydrogen and about 7.13 moles of carbon, or a CH2 as my empirical formula. Is that fine? Cool, thanks, Simran. With that in mind, I'm going to go ahead and look at the mass spectrum. In the mass spectrum, I'm going to see that the parent peak is right here at 70. That parent peak is going to tell me what the molecular formula is. I'm going to take the mass of the molecule divided by the mass of the empirical formula, and I'm going to find out that there are 5 empirical formula units present, or that my molecule is C5H10, or that what's giving this peak is C5H10 and a plus. Now from here, we can lose 15, which is the loss of a methyl. If we were to lose a methyl, we would have C4H7 plus. We can also lose that looks like 29 to me. And a loss of 29 is the loss of either a CHO or the loss of a C2H5, an ethyl. Because there's no oxygen present here, it has to be the C2H5 that we've lost. And so this must be C3H5 and a plus sign. So again, in the mass spectrum, the only ions I can see have positive charges. So in phase 1, we deduced the empirical formula of our hydrocarbon as CH2 using the percent data. In phase 2, we found the molecular mass was 70. So we were able to use the molecular mass and the empirical formula to find out the molecular formula C5H10. We now know that there are 2 fragments we're going to have to be able to find in our molecule, that it has to be able to lose both a methyl and an ethyl to create the C4H7 plus and the C3H5 plus. The IR spectrum is not particularly useful. The IHD here is going to be equal to 2 times the number of carbons plus 2 minus the number of hydrogens divided by 2. The IHD is 1. There is 1 double bond in this molecule. I actually see evidence of that double bond right here. If I look at the IR data, I find that a peak around 1650 is a sign that there's a C double bond C present. So the IHD indicated that I had 1 carbon-carbon double bond, and the IR spectrum corroborated that. I also see a whole lot of structure in that skinny peak around 3000. That's just evidence of some CHs. So I have a molecule that has a formula C5H10. It contains 1 double bond. It has a methyl and an ethyl fragment, and I'm trying to draw it. So I'm going to have to go to the NMR data. The NMR data is showing that there are 4 chemical environments. That's because there are 4 regions where there are peaks. 4 chemical peaks, sorry, 4 chemical environments. And in those 4 chemical environments, the number of hydrogens has been given to us. There are 2 chemical environments with 3 hydrogens and 2 chemical environments with 2 hydrogens. That first peak on the right-hand side is a triplet. A triplet means that there are 3 peaks there. If I use the n+1 rule, that means it has 2 neighbors. The second peak that has an intensity of 3 hydrogens, that's what 3H means, is a singlet. That means it has no neighbors. So it looks to me like I have 2 methyl groups. One of the methyl groups is going to be next to a CH2, and the other methyl group is going to be next to a carbon that has no hydrogens. As I move toward the left, I see a 2H quartet. The 2H quartet has 3 neighbors. That's 4 for the quartet minus 1. So, unsurprisingly, these 2 things are next to each other. They make that most common of all peak patterns. The triplet next to the quartet is the sign that we have an ethyl group. We already found that ethyl group when we saw the loss of 29 in our mass spectrum. The last thing I see is the 2H singlet. That's 2 hydrogens with no neighbor. So now we have to start drawing. I need to have an ethyl group. And there needs to be a carbon that's attached to no hydrogens. Now, this carbon that's attached to no hydrogens is going to need to be attached also to a carbon that contains 2 hydrogens. So I was thinking about doing that. So this is my this is my triplet, 3H. This is my quartet, 2H. Then I have a carbon that's attached to nothing in terms of hydrogen atoms. So these 2 H's will not be split. So these 2 H's would correspond perhaps to this. And I could put another methyl on there. and that could correspond here to that. So if we look at this again, I'm hoping that what I'm going to find is that there are 5 carbons, and I see 5 carbons. I hope that I'm going to find that there are 10 hydrogens, and I see 10 hydrogens. And then I hope that I'm going to see 4 different chemical environments. I tried to denote those with the different shapes. And then I want to make sure that that splitting is correct. So when I look at the circles are going to see the squares, and they should appear as a triplet. The squares are going to see the circles, and they should appear as a quartet. The triangles are going to see nothing at all, because when they look at their carbon neighbor, there's no hydrogens on it, so they'll be a singlet. And the methyl stars are going to also look at that same carbon, see nothing on it, and appear as a singlet. So that is, in fact, our structure. Our structure is going to be 2-methyl-but-1-ene. It's going to address each of the 4 parts of deducing a spectrum. That was the IR, the mass spec, and the NMR. So that's how I used the HL content. It allowed me to deduce this neighbor thing. I can get a really long way before I have to look at the splitting. And the splitting is a rich area to understand more about, but the N+1 rule makes it a little bit easy to use, to apply, kind of fast. We're really going to count the number of peaks we see, subtract 1, and know something about the neighbors. If there was a single thing I took away from the splitting patterns, it would be if I have a triplet and a quartet, that it's going to be relatively confident that I have an ethyl group present. Knowing that I had the double bond from the IR, knowing that I had an ethyl group and a methyl group that fell off in the mass spectrum allowed me to put this molecule together relatively quickly, maybe too quickly because we're running out of time, but I hope that that helped. So Simran's trying to come up with a strategy for this and is saying that the first step was to find the empirical formula. The second step was to find the molecular formula. And the third step was to use the NMR data to try to draw the molecule. If I wanted to add to that, I would say that we looked at the IR data and found that carbon-carbon double bond, and that we looked at the mass spectrum data and we had evidence that we were going to see both a methyl group and an ethyl group be able to fall off. That is, we saw both the loss of 15 and the loss of 29 fragments, and that helped me to put this ethyl group and this methyl group together. Now, you could certainly say that you knew that there was an ethyl group because of the NMR quartet and triplet pattern, or that you knew that there was a methyl group because of this 3H singlet. So the data can be a bit reinforcing or repetitive. But I think that it's lovely that you can solve these problems almost iteratively. So you can look at the IR and maybe you'll see that CC double bond. And if you do, that's fantastic. But if you don't see it yet, you could calculate the IHD. And that will remind you, I've got a CC double bond. And so now I can apply that and get my mark for what's present at 1640. If I see the ethyl group present in the NMR, I can go over to the mass spectrum and say the reason that there was a loss of 29 to get to that 41 peak is because of that ethyl. And so I do not have to do these problems in an order if I don't know what I'm looking at. I find the NMR, as Simran was saying, to be the most useful in terms of deducing the structure. And so often I will skip ahead to it because it's often the last one that's given, and try to just write a few notes about what I'm looking for in the other spectra. That's the last problem I'm going to be able to solve, I guess, but I'm going to sit here and answer questions as long as you're interested. The first one I see is, what does parts per million mean? And it means, how does the shift of this compare to the shift of tetramethylsilane? So it does mean parts per million, and it's just how the frequency of your spin flip is different than that of our internal standard TMS. We put the TMS peak at 0. As far as I know, the full meeting will be recorded. I know it's recording now, and it was recording then. So I am optimistic that this is going to work out. I'm sorry my internet crashed, but we're back. Thank you so much for being patient with me. The TMS has been shown in the spectrum on occasion, but I would say in the last in the last 2 years, I have not seen the peak at 0 being shown on the NMR. When I use the word shift, I'm talking about the placement of the chemical environment as compared to 0. So this axis that's measured in parts per million, the words for it are chemical shift. And so something that is further to the left on my graph is more shifted. Vanessa, I love that sentiment. Good luck to everyone. I hope you guys have a wonderful exam season. Thank you so much for being patient with me and asking good questions. I hope you guys have a wonderful day. It's fine. I'm looking at section 29. I have my data booklet open right here, so I was just going to try to put it on my screen where I could actually see it. So 29 is the Van Arkel-Catellar triangle, and it's used in option A. So Simran, if you're doing option A, it's a way of finding out what type of bond you're looking at by looking at some electronegativity averages and differences. And if you're not doing option A, 29 doesn't matter at all. That's fine, Galena. I'm sorry I missed it. So I think what you said is exactly true. If a question's worth 1 mark, the state symbols are traditionally not expected. They're only expected if it's worth 2 marks or if the question explicitly says including the state symbols. So if it's a 1 mark question, I think you're good to go. But if it either expressly asks for them or if it's worth 2 marks, we traditionally have to put it. I would say the place where I'd be most worried about state symbols is when you're doing the combustion. You want to make sure that you're always making liquid water. Okay, thank you so much, everyone. I hope you have a wonderful exam season and a wonderful day or night. Bye.